Alright, in our first numerical example of how to apply our famous bending stress equation, hey, what is that? That is sigma equals my over I. Technically that would be a minus my over I, right? We go up positive from the neutral axis with a positive bending moment, and we end up with a compressive or negative stress, right? We've got two cross sections that would appear to have the same area, right? 6 times 2 here, 6 times 2 there is 24. 4 times 6 is 24. Same amount of area, but arranged differently. Same bending moment, 50 kip foot. We're going to find a variety of things here on the stress distributions for each one. Right? So let's go work on the rectangle first. We're going to find the flexural stress at point B. Here's our model that we're going to use. We're asked to find sigma. The normal stress is equal to minus my over I. That means we need to know the I, and we got to find the y. We've already been given the moment. Right? And remember, the neutral axis is at the geometric centroid of the cross section for elastic behavior. That's of course easy to find for our rectangle. It's at half the height, or 3 inches top and bottom. Right? Point B is 1 inch down, so that means the distance from the neutral surface, or the centroid, is going to be a plus 2 inches. Right? So let's do this one first. Let's call this A and this one B. Right? So for A, we have to find our second moments of area. Oh man, we got to do those too. Well, I for that one is of course 1/12 BH cubed. And that's the centroidal one, right? 1/12 of the base, 4 inches, times the height, 6 inches cubed, and that's going to be 72 inches to the fourth. Right? So for A, then, our stress at B will be equal to minus my over I. That's equal to a minus 50 kip foot, which I'm going to convert into kip inches, times our y, which will be a plus 2 inches, and then all divided by our inches to the fourth of 72 inches to the fourth for the second moment of area. Right? Notice the units that we're going to get. We have kip inch squared in the numerator, and we have inches to the fourth in the denominator, so that'll leave us kip over square inches, so that's KSI. And so the rest of this will be then 50 times 12 times 2 divided by 72, and that equals, and let's see, this was a minus 16.67, and so about a minus 16.7 KSI, minus indicating that we have a compressive stress. So sigma B equals 16.7 KSI in compression. That's for point B, for the left-hand one. Right? For the other ones, then it's the same kind of thing, minus my over I. We still have minus 50 kip foot times our 12 to get us into kip inches, and then we got to get our y distance. Now, this one has a centroid. You need to work through this yourself, but that centroid is at 3 inches down. How did I know? Because I did the math myself. Right? And since B is 2 inches down, that means our y distance here this time is a plus 1 inch. Right? So that's we're ending up with kip inches up there times a 1 inch there, and then we're going to divide, and it'll turn out that this I, using parallel axis theorem, for this one is going to be 136 inches to the fourth. Right? How'd you know? Because I did the math. Where did that come from? Is that I with respect to point B? No, it's the cross section. Maybe that was a poor use of symbols there. But it's this centroidal second moment of area for this entire cross section. It's 136 inches to the fourth. So we have some interesting things happening here. Same moment, we're closer to the neutral axis, and we have a bigger second moment of area. We should expect a lot smaller stress as a result. and indeed we do, we get a stress that is still in compression, but 4.41 KSI in compression. So about a factor of 4 smaller. That's kind of a pretty big deal. Same amount of area, just arranged differently, has a pretty big effect. Interesting, right? Then let's ask the question, what's the maximum flexural stress in the cross-section? Right, and then we're going to sketch the flexural stress distribution. I actually kind of want to do that first. Right, for A, that would look something like this. And note, in the first step, we found that this 16.7 was happening right about there. That was 2 inches up from the bottom, right? And this, because we have a symmetric cross-section, that means that the max is going to be the same on both edges. One's compression, one's tension. That's important. But to get to the max, we could do this a couple different ways. Since we know where the neutral axis is, we could use proportionality to get the other one, right? So this sigma max up here would be 3 inches divided by 2 inches times 16.67. That would be the congruent triangle. And that would be 25 KSI. Right? Now, the other way to do it would just be go back to this sigma equals my over I. Now notice this time it'll be sigma equals really MC over I, and we'll, hey, let's go down to the bottom, right? So this is a minus, so minus, and that's 600 kip inches. We've done this a number of times, so I'm not going to write all those unit conversions out. And the C now is a downwards, so that's a minus 3 inches. Right, so that was kip inches, all over the 72 inches to the fourth, and so that's going to be 1800 divided by 72, and what do you know, that's 25 KSI again, in tension. Right? So that's that one, a nice symmetric cross distribution, and that also told us what the maximum was as we did that. Now look what happens when we go to this asymmetric cross-section, a little bit taller, and the neutral axis is at 3 inches from the top, and I draw that straight line, and notice that the bottom one is going to be larger. Right? And so we know in this case that at 1 inch away from the neutral surface, we're at 4.4. It was actually 4.41 KSI. And again, we could use linear proportionality to get out to the outer, but let's just do the calc, show it from down at the bottom. Sigma max here in tension is, okay, MC over I, but C to the bottom, so that's 600 kip inches. We've got the C that's downwards as a minus 5, minus times a minus, so I'm not going to write that, divided by the 136, and that's going to be then the 3000, that's 5 times 600, divided by 136, or 22.06 for that max on this one. And because I'm a good little soldier, I'd really like to know what we've got up at the top. And so let's see what 5 is to 3. That'll be smaller, so times 0.6, that's going to be 13.2 KSI up here at the top, and that of course should be exactly 3 times this other one because it's at 3 inches away compared to just 1 inch away, and we do that and we get back to what we had here. So it's all looking very good. That's how you do all of those. Now, if you ask for the yield moment, that'd be the moment that would cause first yield on the outer fiber, and that would be down here at the bottom on this one. Then you would set the stress to be equal to the yield stress, and then you would calculate the moment that would go along, so that would be I times sigma divided by C.